Hello, this is video 2-3. I chose problem number 16, and let's get started. So, ignore the graphs for now, and let's just pay attention to the question. A disc thrower accelerates a discus from rest to a speed of 24.9 meters per second by whirling it through 1.21 revolutions. Assume the discus moves in the arc of a circle 0.96 meters in radius. So, first off, write our givens. If the final speed of the disk is 24.9, then I'll call that the final tangent speed because when the disk is released from the circle, when it's no longer in circular motion, I suppose, it's traveling at 24.9 meters per second. And then we convert the revolutions they give us to radians, so because that'll allow us to work with that number, that quantity, and R equals 0.96. So let's graph as soon as possible. Since the disk will be accelerating, and I'll start from actually this angular acceleration time graph first, because I think it's a good place to start. We know that there's acceleration, no mention of calculus or anything, and the web design doesn't usually deal with that, so it's a constant acceleration. Constant acceleration means that our velocity will be increasing. Our angular velocity is important. So angular velocity increases steadily, and so if velocity is increasing, more radians. Yeah, okay. Sorry, you got to get used to the new terms, but more radians are covered in less time. Okay, so part A asks us to calculate the final angular speed of the discus. Have our givens that I went over. We know the formula: angular speed equals regular speed or linear speed over the radius. We plug in those two numbers, and then we get 25.9 radians per second. And what I like to think about this formula, it's kind of a transition or a translation to angular kinematics with that dividing by the radius there. And then we put that in WebSign, it's all good. So B is a little tougher. It's determine the magnitude of the angular acceleration of the discus, assuming it to be constant. So we're going to have to find this angular acceleration value. And we know, again, constant, no calculus, be happy. Disk starts at rest. They tell us that in the problem. And we don't have time, so we're going to have to use a angular kinematic or rotational kinematic that suits us. I chose to do this one because we do have final angular speed. We do have the initial speed. We don't have acceleration. Apologize, we're solving for that. Change in radians. We have that from up here. And again, this is like the linear kinematic that we know very well. We manipulate to set it equal to angular acceleration, plug in our values, and then angular acceleration equals 44.2 radians per second squared. C is largely the same idea as B. It's asking us to calculate for time. So again, speed, initial speed, angular acceleration, time, set it equal to time. Plug in the values, and there you go, you get time. So takeaways for this problem is pretty simple in nature. It's a good problem to pull the concepts of the angular kinematics together. And don't overcomplicate. Make sure you list your givens and use your formulas from there. And I think this is a good question, or good problem to ease people into the rotational kinematics. It could be, I mean, for me, I was just like really, like I kind of understood what it was going for, but I was a little confused. And I think practicing these and really realizing that it is just kind of some form of linear kinematics, at least in the sense that you have your angular acceleration, which is new to us, and you can put that in the angular kinematics, the rotational kinematics, which is really helpful. So I'm going to go grab a a photo of the web sign problem completed, and then I'll conclude the video. Sorry about the cut, but here is those three values plugged into the website, and it's all good. Thank you for watching.